If you are in my honors geometry, this is a review. If you are in my regular geometry, this is new stuff. We haven't touched upon this yet. If you are in Mr. Abdelhadi's regular geometry class, I believe he mentioned that he was able to get through circles more successfully than I have. We will get to circles after EOC. Unfortunately, time just didn't permit. So here we go. Starting off with stuff that you've seen before. Circumference of a circle is a formula that's not going to be on the reference sheet. Circumference of a circle is 2 pi r, or pi times diameter. It's the exact same thing. If you are finding the measure of an arc, the measure of an arc is the same as the measure of its central angle. However, if you're talking about the length of an arc, you're talking about if you were to take that part of the circle and cut it off and put it on a ruler, how long would it be? Think about it. It's a part of the circumference. It's a fraction of the circumference. And we're going to talk about how to find that fraction, how to use that fraction. Same principle applies if you're finding the area of a sector. If you wanted to describe a sector to your friend, you would probably describe it as a slice of the pie, slice of the pizza. And since the area of a whole circle is pi r squared, if we're finding the area of a sector, since a sector is a part of a circle, we would just be finding a fraction of the area of the circle. And again, we'll talk about that. The diagrams don't show up very nicely on my screen, but they should be showing up very nicely on the piece of paper in front of you. Okay, so the fraction of the area of the circle, fraction of the circumference of the circle. Here's the fraction that I'm referring to. How many degrees is it all the way around a circle? 360. So the fraction that you're taking of the circle is the fraction that that angle is of 360. So it's always that arc measure over 360 being multiplied by either the circumference or the area of the circle. So same thing, arc measure over 360 times the area of the circle.
Wait, is that times C or minus C?
Times C. It's a fraction of the circumference. Okay, so in parts A and B, where I'm asking you for the length of each arc, we could find the whole circumference first. The circumference in part A, since they've given us that the diameter is 9, that circumference is 9 pi. And since I'm asking for the length of arc CD, let's first talk about what is the measure of arc CD. What is the measure of arc CD? It's 90 degrees. So you would take that 90 and put it over 360. And that's the fraction that you're taking of the circumference, 9 pi. Now, by all means, before did everyone sign in? Thank you. By all means, if you want to reduce this fraction before you go multiplying it by 9 pi, I would suggest it. You're going to be dealing with much more manageable numbers. So 90 over 360 reduces to 1/4 that I'm taking of 9 pi. And if the whole concept of, oh, she's telling me to take a fraction of something, and I hate fractions. First of all, you got to get over it. And then second of all, remember that multiplying fractions really isn't the most awful thing in the world. Multiplying fractions is straight across the top and straight across the bottom. So if it helps, put that 9 pi over 1, and straight across the top, we have 9 pi, and straight across the bottom, we have 4. And we could certainly leave our answer like that, 9 pi over 4 centimeters. Done. It's just a fraction of the circumference. Same idea in part B, but be very careful. In part B, I'm asking for the length of arc STR. Look carefully at the diagram. What is the measure of arc STR? Say it again. 260. The measure of the arc given to us is the measure of arc SR, 100. Be very easy to make the mistake of thinking that that 100 is what you're doing something with. What you need to realize is that it's 360 degrees around the circle. So what's left is STR. That's 260 over 360.
Wait, I'm confused. Why would it just be 260? Because it's this one, it's 360. Yeah, but wouldn't it just be 260?
The measure of the arc is 260.
Oh, okay.
What the problem is asking us is for the length of the arc. Okay, so it's a fraction of the circumference. My radius is given to me as 4, so that means that my circumference is 8 pi. Once again, I would advise reducing your fraction whenever possible. If reducing fractions is something, however, that makes you kind of hyperventilate, then don't. By all means, you can just multiply straight across the top and multiply straight across the bottom as is. You'll end up with the same answer. Okay? You might have to, divide at the end.
Take the zeros out.
Absolutely, you can take the zeros out and then realize, hey, these numbers are still even, so I know they're both going to be divisible by 2. So I could reduce this to 13 over 18 times 8 pi. And if you remember from middle school fraction calculations, you can cross-reduce as well. So this reduces to 4, this reduces to 9,
Wait. Wow.
because I can reduce across the diagonal.
By 2?
8 and 18 are both divisible by 2.
Could you do by 8? 8?
Is 18 divisible by 8? You absolutely can. Okay, so we'd have 52 pi over 9 feet. In the problem on the right side of the screen, I'm asked for the area of the sector. The area of the sector is a fraction of the area of the circle. So be really, really careful. When my students were doing this in class, some students were mixing up their formulas and they were asked for the area of a sector and they were using the circumference of a circle. Be really, really careful. Don't do that. Make sure that you're reading the question. If I'm finding an area of a part of the circle, then maybe I want to find the area of the whole circle first. So let's find the area of the whole circle. Area, remember, is pi r squared. So the area is 9 squared, which is 81 pi. What fraction of the circle am I interested in? The 84 over 360. And by all means, if you already reduced that fraction, fantastic. But I want to make sure I'm going step by step for everyone. 84 over 360 is what I'm going to be multiplying by that 81 pi. And again, you could totally reduce that fraction before multiplying it. You can multiply it as is, just in the interest of accommodating everybody and doing it the way maybe someone else would do it. Let's leave it the way it is and multiply it. So when I do, I have 84 times 81, which is 6804 pi over 360. And I could take that 6804 and divide by 360 and get 18.9. Tack on the pi. Square millimeters. Okay, but again, the main thing that I want to get across to you on this screen is if they ask you for the length of an arc, think of it just as a fraction of the circumference. If they ask you for the area of a sector, it's just a fraction of the area of the circle. Okay? Got from the screen what we need. Couple of things about circles. I'm kind of going through a whole unit in 40 minutes and chopping out pieces that I think we can do without for right now, but tangents are a concept that you could very feasibly come across. A tangent line to a circle is a line that touches the circle at exactly one point. One of the properties of a tangent is that when you draw a radius to the point of tangency, it's going to be perpendicular to that tangent line. So one of the nice things about tangent lines is very frequently you end up with right triangles. Maybe you end up with some Pythagorean theorem. But at any rate, in this example on the left, notice how simple the question is that we're being asked. This is a triangle. Tell me again what we know about the angles of a triangle. We've talked about it before. 3 angles of a triangle add up to 180. I know that 38-degree angle. I now know that angle D is a right angle. So I add them, subtract from 180, and that's going to give me the x that I need to solve for. So x is 52. The Pythagorean theorem that shows up in the diagram on the right is a little bit messy and a little bit algebra heavy.
Wait, how do you know that one's a right angle?
Because it's tangent. And because OD is a radius to that point of tangency. It's one of the properties.
Alright.
Okay? So in the diagram on the right, I have a right triangle. And I know when I have a right triangle and I'm dealing with the side lengths, I can use Pythagorean's theorem. But you want to be very algebraically careful here. Okay, x squared plus 24 squared, nothing too difficult there. It's when we get to the hypotenuse that students tend to cringe a little bit. The hypotenuse, notice, is x plus 18. And when I'm using that Pythagorean theorem, it's x plus 18 that I'm squaring. It's a common but dreadful mistake to think that x plus 18, quantity squared, is just x squared plus 18 squared. It's not. Think about what it means to square something. It means that you're multiplying it by itself. So I could think of this as x plus 18 times x plus 18. Any math words coming to mind? FOIL, first, outer, inner, last. Here's what I mean by that. First times first, x times x is x squared. Oops, it's a plus sign. Outer times outer, that's x times 18, which is 18x. I multiply together my inner terms, that's another 18x. And I multiply together my last terms. Oops. Sorry. And 18 times 18 is 324. And then, by all means, I can simplify the left-hand side and get x squared plus 256. No, not 256. 576. Okay, so some of you might be looking at these x squareds and thinking, oh boy, I'm really in trouble. But we get lucky in this instance because look at what's going to happen in the next step to those x squareds.
They all go together.
if I try to subtract x squared from one side of the equation, it's just going to cancel out on the other side of the equation anyway. So I don't have a quadratic, which is a happy relief here. So now we have 576 equals 36x plus 324. Absolutely. My next step is going to be to subtract 324 from both sides. I get 36x equal to 252. And when I divide both sides by 36, x is 7.
7.
Congratulations. Okay, so I thought that this was a good example for me to throw in there using a property of a tangent, bring a little algebra back into the mix, and giving you a moment to get what you need from this screen. Okay, another property of lines that are tangent to a circle is that if I have two tangent segments coming from the same exterior point, those two tangent segments will be congruent to each other. And I absolutely get that that might be a little difficult to visualize, so that's why I gave you some space here to maybe sketch an instance of that. If I have a circle drawn a little better than that, and I have two tangent lines to it. So again, kind of pretending that Mrs. Clouse can draw better than what you see up here. If these two tangent segments are touching the circle at exactly one point, then these two segments are congruent to each other. So in this problem beneath it, where I'm telling you that circle S is inscribed in triangle LMN, let me clarify the vocabulary there. If you have a circle inscribed in a polygon, that means that the circle is tangent to the sides. So what that gives us is a bunch of tangent segments from a common exterior point. So what I mean by that is that since LR is 8, LO is also 8. So what's the length of NT then? There we go. And the length of TM? Excellent. And so now we know all of the parts of this triangle, and we can just add everything together since we were asked for the perimeter. So the perimeter is 8 plus 8 is 16. 14 plus 14 is 28. 5 plus 5 is 10. Add that all together, I've got 54. And there's no units in the diagram, so I'll just write units. We've talked a little bit, and we talked a while back at the beginning of the year, my students anyway, about how the measure of an arc in a circle is the same as the measure of its central angle. Another kind of angle in circles is called an inscribed angle. And I don't mention it in the notes, but you might want to add to your notes that an inscribed angle basically has its vertex on the circle. Okay, so let me make some more space up here. An inscribed angle has vertex on the circle and the sides are chords. So a very convenient thing about inscribed angles is that we can find the measure of an inscribed angle by taking half of the intercepted arc. Okay, so again, the measure of an inscribed angle is half the intercepted arc. And if that phrase intercepted arc is a little bit weird for you, my students are familiar with my saying, what is Pac-Man eating? And here's what I mean by that. For example, angle B, see angle B here? I traced it badly, but hopefully you see the angle B that I'm referring to. That's an inscribed angle. Do you see Pac-Man's mouth? Pac-Man's head is really, really big. What's Pac-Man? Do you see Pac-Man?
What about angle 52?
Well, hold on. Angle 52 is also an inscribed angle, and we'll talk about that in a moment. But since I'm kind of exposing some of you to the vocabulary of inscribed angles for the first time, I just wanted to talk about angle B first. So, what's angle B eating? 56. So, according to what I just told you up here, angle B is just half of that. So, B is half of 56. So, that's 28. Okay, Sophie was asking, what about the 52? You're absolutely right, that 52 is an inscribed angle, and we are going to use it in order to find A, which is an arc. Now think about it. If an inscribed angle is half the intercepted arc, what would I do to an inscribed angle if I wanted to find its intercepted arc?
Double it.
I'd double it, absolutely. Okay, yes. Is that a question? No. Okay, so guys, if I double 52, I get 104. Understand what I just found though. This is the 52. It's eating this 104-degree arc. How am I going to use that information to find the measure of A? Subtract the 56. Yes. So A is 104 minus 56, which is 48. Another convenient property about inscribed angles, we talked a couple of moments ago about a circle that was inscribed in a polygon. In the next diagram, we've got a quadrilateral inscribed in a circle. Property of a quadrilateral inscribed in a circle is that the opposite angles of it are supplementary. So, looking at this diagram, if I look at angle 4, again, if the prospect of an inscribed angle and what is it eating is weird to you, again, think about Pac-Man opening his mouth up wide, and what is the arc that he's chomping on? Angle 4. What is the arc that angle 4 is eating?
2.
It's an arc, or arcs.
60 and 80.
The 60 and the 80. Okay, so the measure of angle 4 is half of that 60 plus 80. So 60 plus 80 is 140. Half of that is 70. So based on that, based on angle 4 being 70, and the property that I just gave you above that diagram, what's the measure of angle 2? No, Dylan.
Oh wait, no, 110.
110. Okay, some of you might be looking at angle 1 and angle 3 and thinking in terms of, I don't know the measure of the arc that it's eating. But notice that that red segment connecting them, this segment here, what is that to the circle? What is that red segment to the circle? Is you can think of it as bisecting the circle. What I'd like you to realize is it's a diameter, And as Callie so beautifully put it, it is kind of bisecting the circle. And how many degrees is the whole circle? 360. So do you see that we have two semicircles? And what's the measure of a semicircle? So what's the measure of angle 3? Measure of angle 3.
Oh, I thought you meant. I have no idea.
Okay, let's put it all together again. It's going to be 90. Let's put it all together. Callie told us that this red segment is bisecting the circle. That's one way to put it. Circle is 360 degrees all the way around. And one of the lovely ladies over there told me that means that this semicircle is 180. Angle 3 is an inscribed angle intercepting that 180. And inscribed angles are half of their intercepted arcs. So that's why measure of angle 3 is 90. And the measure of angle 1 is also 90. Gorgeous. And what we will just barely have enough time to talk about is the last topic on your notes, which is the equation of a circle in the coordinate plane. Now, again, some of you already know what the equation is. Some of you might not be aware. First of all, let's rehash. Distance formula is x1 minus x2 squared plus y1 minus y2 squared. So if you needed to find the distance between 2 points, and again, myself personally, I know I haven't talked about this in my regular geometry class. If you're in my regular geometry class, please make sure that you write that down. I can't speak for Mr. Abdel Hadi's regular geometry class. I think he may have gotten a little further than I did. Okay, so in a circle, does it make sense that the radius of a circle is the distance, I can use the distance formula, from the center to a point on the circle? So, you know what, let me just give you that standard form of the equation since we're tight on space and time. The equation of a circle is r squared equals x minus h squared plus y minus k squared. That's what the equation of a circle is going to look like.
What's the first one?
The blue equation that I gave you up there, that's the formula for distance. Distance between any 2 points on the coordinate plane. You can use distance formula to find any distance in the coordinate plane. All right, so the first problem in which we're using this standard equation for the circle in the coordinate plane, I'm giving you the center and I'm giving you the radius. So all you're doing is taking those values and plugging them in. Okay, once again, h comma k is the center of the circle. So we have x minus negative 6 squared plus y minus 8 squared equal to 5 squared. And just be aware that if this was a problem on the EOC, they would expect you to clean up what you can easily clean up. Please understand. It'd be very unlikely that they would expect you to square this and FOIL this out and do wild and crazy things to it. At most, I would imagine they would want you to clean up this minus and negative so that you have x plus 6 quantity squared, leave this y minus 8 quantity squared equals 25. And that's what the equation of the circle would look like. You could also very reasonably be asked to go in the opposite direction. They could give you the equation of a circle and ask you to identify the center and the radius of it. They could, considering the kinds of questions that this FSA allows that previous end of course exams have not, they could even give you a grid with a circle tool and say, graph this circle. Okay? So in order to graph the circle, you got to know where the center is, you got to know what the radius is. Notice something about this center that they gave us in the previous problem and how it looks in the equation. Notice very carefully that the x-coordinate was negative, but what do you see in the equation? You see a positive 6. Okay, so just have that in mind, that because the standard form is x minus the coordinate, what you're looking at in the equation is actually the opposite of what the coordinate is. So in this equation, again, it looks a lot clearer on your notes than it does on my screen. In that equation, keeping in mind that the coordinate is the opposite of what you see, what is the center of the circle? What comma what? It's 3, negative 2. It's the opposite of what you see in the equation. Okay, so the center of the circle is 3, negative 2. What's the radius of the circle? It's 6. Remember that the standard form of the equation, this number over here is the radius being squared. So in the equation we have to unsquare it, also known as square root, to get that the radius is 6. Last kind of question I want to address. What if they don't give you the radius? In the last kind of problem that I put on your notes for you.
Oh, they're backwards.
Oh, sorry about that.
You're good.
Did that yesterday. Okay, so in this problem, again, in order to write the equation of a circle, you need to know the center and you need to know the radius. Well, we know the center, but we don't know the radius. But again, keep in mind where that equation of a circle came from. It comes from the distance formula. So, my radius is the distance between these 2 points. So a little bit of practice with distance formula for those of you that haven't seen it before in regular geometry. Okay, so 4 minus 2, that's this minus this, squared plus 2 minus negative 3, that's this minus this. Please, please, please realize, and I'm a little annoyed at the numbers that they use because it'd be very easy for a student to misunderstand it and think it's x minus y and x minus y. It's definitely not. Never ever do you subtract x minus y. It's x minus x and y minus y. And when I clean this up, 4 minus 2 is 2. 2 squared is 4. Plus, this is 2 plus 3, that's 5. 5 squared is 25. So I know that the radius is 29. And one of the things that I stressed heavily to my students is that there is absolutely no reason to touch my calculator at this point and try to figure out what the square root of 29 is. Because look at what the equation of a circle does to the radius. What does the equation of a circle do to the radius? It just squares it back anyway, okay? And you should know that when you have a square root and a squared, those two things cancel each other out. So then your equation is just 29 equals x minus, I've got 2 points here. Which one am I using? The center. Make sure that you're using the appropriate point. It's this guy. So x minus 4 squared plus y minus 2 squared. And that's it, that's the equation.